Hi, I'm Joe Romano,
And my name's Kyle Maroney
and we're Little Tomato Robotics.
from Somerville, Massachusetts.
Our project is multi-athlete, sport-specific motion and readiness analysis. Hi, my name is Joe. I graduated with my PhD in mechanical engineering in 2012 from the University of Pennsylvania, focusing on haptic interactions and analyzing acceleration vibrations. Currently, I'm a researcher at Kiva Systems where I work on robot manipulation. Growing up, I played a lot of ice hockey in high school and in college. Prior to the UA39 contest, we've been brainstorming ways to integrate the sports and technologies we were passionate about into a fun project, and the 9 Sites announcement was the perfect opportunity to do that.
Hi, I'm Matt DeSico. I'm a software engineer working here at MIT in Boston. I received a BS in mechanical engineering from Carnegie Mellon and a master's in robotics from MIT. When not working, I like to go running and cycling when it's warm and snowboarding during those long, cold Boston winters. You may ask, what does robotics have to do with sports and Under Armour? Well, you'd be surprised. A lot of the sensors that we use in robotics are similar to those inside of a UA39 bug. We've been working on applying signal processing and machine learning techniques to the acceleration data from the bug. We think this can provide some useful insights to athletes and coaches.
Hi, my name's Kyle Maroney. I'm the technical lead of SDK development at Rethink Robotics in Boston, Massachusetts. I received a master's in engineering in 2012 from the University of Pennsylvania, where I was a member of the haptics lab. Previously, I was an engineer and athlete at the University of New Hampshire, where I was an all-conference 3-year starter at defensive end. The Armour39 Challenge has provided the opportunity to combine the knowledge gained during my collegiate athletic career with my experience as a software engineer. We're happy to be able to share with you the results of our efforts today.
We took a unique approach for the development and analysis architecture for our system. We start by configuring the Armour39 devices to stream acceleration data at 100 Hz over Bluetooth Low Energy notifications. A host PC running Linux receives the data through a custom Python class that parses and converts the raw data into a comprehensible format. The data is then pushed in real time into an instance of the MathWorks MATLAB engine for high-level signal processing through custom scripts. These scripts enhance sport-specific features in the acceleration data and then return the resulting action confidences to a Python visualization script and UI front end. The first step after we get data from the UA39 sensor is that we split it into 2 frequency components. A high frequency component, as you'll see here in the green plot in the middle, and a low frequency component, as you see here in the bottom in blue. The purpose of this is to remove any non-zero mean bias from the high frequency signal, such as that from gravity. The purpose of the low frequency signal is to act as an integral term to get things such as velocity sensing over time that we use to compute planar motions, such as shuffling. We then use these 2 sampled frequency components in all subsequent activity detection steps. The first method that we used to try and distinguish different activities from our data was to look at the spectral content. Unfortunately, this did not work out due to the low resolution provided by the UA39 sensor, coupled with the different variety of frequencies that were similarly excited during these motions. The second method we tried was to design custom wavelet filters to detect patterns in the acceleration data. This also proved ineffective because of the restrictions on wavelets of zero mean and squared norm, and was not a flexible enough detector for the interesting signals seen in real physical activities. The approach that ended up working best for our analysis was to design match filters for each activity we wanted to identify. By taking a template from raw data, such as a 1-second instance of a jump as seen here on top, we're able to invert this raw data in the middle to design a custom filter. By running this filter over new live data, we're able to accentuate patterns that match the template and suppress those that don't, which allows us to threshold the resulting vector and identify different motions as seen on the bottom. We created these template match filters for several different motions while playing basketball, the sport we chose to focus on for the UA39 competition. Here you see template filters created for jumping, running, and shooting. Athletes perform these canonical motions at a variety of different speeds during a game. In order to capture this, we dynamically warp the timing of each template between -30 and +30% of the original, and sum the result of each of these filtered signals. Shown here is an example of what a coach's tablet interface might look like. All the data is simulated, but it does show the basic information that the app will display. Each row contains a unique player that the user has indicated is in the game. Cumulative stats like heart rate, playtime, and shot totals will be actively updated throughout the game, and simple strip charts give an overview of what players are doing. Here we see an example strip chart of fatigue measure of each player and some example detectors for jumping and running that update in real time over a short window of a few seconds of gameplay. As we develop new detectors, this interface would expand and become a rich source of information for coaches to make intelligent decisions.